Can you tell me what's the electric field the small charge creates here? So let's say dE. dE will be 1 over 4 pi epsilon 0 times dq divided by the distance squared. But what's the distance now? It's x plus d. It's the whole distance from my small charge. So this is going to be x plus d. So it's going to be x plus d squared. Now, what is the electric field? It's going to be integral dE. So it's going to be integral 1 over 4 pi epsilon 0. dq is lambda times dx. So let me write lambda x plus d squared dx. But so far I haven't actually written down the expression. Whenever I'm writing down an integral, it has to be a definite integral. I cannot just leave it as an indefinite integral. So what are the limits of my integration? Which is the first small section I take? It's starting here. And the final small section I'll take will be at infinity. So this is going to go from 0 to infinity. Okay. Lambda over 4 pi epsilon 0. Integral from 0 to infinity. 1 over x plus d dx squared. This is a... How many of you feel confident enough to be able to evaluate this integral? Come on. So how many of you have taken Math 101 and passed? So, come on, this is a simple integral, right? How am I going to do it? Just by a simple substitution. So let me call u as x plus d. Then du would be just dx. The only thing I need to be careful about are the upper and lower bounds, the limits. If x is equal to infinity, u is also infinity. But if x is equal to 0, u is d. So by making this change, lambda over 4 pi epsilon 0, integral from d to infinity 1 over u square du. How about this integral now? That is easy enough, I guess. So it's going to be lambda over 4 pi epsilon 0 minus 1 over u evaluated at infinity and d. At infinity, minus 1 over u is 0. So it gives me lambda over 4 pi epsilon 0 d. That is the magnitude of my electric field. Did I reach my goal? No. Really? Why not?
There's a direction.
Okay, but I already gave the direction. So I would say, okay, I reached my goal. But that's an important point. Every time you must make sure that you answered everything that's asked in the question. So I gave the direction, I gave the magnitude. What was our second check? Units. We need to make sure this expression is in units of electric field. Now I know that charge divided by epsilon 0 divided by meter square gives me an electric field. So what do I have here? What was the unit of lambda? It was one-dimensional charge distribution. So it was coulombs per meter. So the lambda over d unit will be coulombs per meter square, and that's exactly what I need. 1 over epsilon 0 unit times 1 over meter square, coulomb per meter square, is Newton per coulomb, which is the electric field units. How about some limits here? what would you expect if I go far away from this half infinite line? I would expect the electric field to go down. Okay, that makes sense. So D going to infinity, E goes to 0 makes sense. And unfortunately, or fortunately for this problem, there isn't any other limit I can actually check here. Okay, that's pretty much it. Any other questions about the quiz? No? Okay. Let's solve another example. How about not taking a half infinite line, but fully infinite line of charge with uniform charge density lambda throughout, and trying to find the electric field at a point P, which is a distance r away. So find the electric field a distance r away from an infinite uniformly charged line. So again, I know this is very simple, but the geometries are going to get more complicated, so I keep asking the same question. Does everyone understand the geometry here? I have an infinite line, and I'm at a point P, and the shortest distance to that line is r. Okay? So I would like to find out what the electric field at this point is. First, let's talk about the direction. Then let's try to calculate the magnitude. Any guesses on what should be the direction of the electric field? This way is not. So try to express this better. I'm sure it's that way, but. So this is my line, and this is the electric field vector. Do you expect it to be in the same direction? No. It should be perpendicular. Can it have a component along, up, or down? Why not? By symmetry, right? Up or down cannot be chosen by the electric field. So I'll just directly say, by symmetry, E field is perpendicular to the line. So I expect E to be this way. Let me call this to be the x-axis. I'll say E is E magnitude I hat. But now, how do I calculate the magnitude? Again, instead of a continuous line, if I had just point charges like beads on a wire, I would do a very simple thing. I would just calculate the electric field of each of them and then add. But I have to be careful. The electric field is an additive quantity, but it's additive as a vector, not as a scalar. So I have to be careful about which component of the electric field I'm actually calculating. All right? So we'll do the same thing over and over again. Let me call this distance y. Okay? And take a small section which has length dy here. Now, it's going to create an electric field dE like this. But am I interested in the total length of the electric field, or am I interested in the x component of this electric field? I'm interested in the x component because y components are going to cancel. Coming from the top and coming from the bottom, the x components add up, y components cancel. So let's try to calculate not dE, but just dEy. Okay. dEx. You're right. Thank you. The first step here is to find out how much charge I have here. How much charge do I have? Lambda times dy. Great. Then can you tell me what's the magnitude of the small electric field created by this small section? Well, I always have the 1 over 4 pi epsilon 0 in front. I have dq divided by the length, but which length? The length from the charge to the observation point, which is here. The distance from the charge to the observation point. So it's going to be y squared plus r squared. This is the magnitude of the electric field. Let us be careful. I'm actually interested in dEx, which will be dE magnitude times, if the angle here is alpha, the angle it's going to be cosine alpha. Okay? But cosine alpha I can actually write in terms of the larger triangle here. Cosine alpha is r divided by square root of y squared plus r squared, right? Am I right? Good. So dEx is 1 over 4 pi epsilon 0. dq is lambda times dy. And I have y squared plus r squared. And instead of cosine alpha, I'll just write r divided by y squared plus r squared to the 1/2. So maybe I can write this after a bit of tidying up as y squared plus r squared to the 3/2 dy. Now, what's the next step? I need to integrate this. So Ex is integral dEx. So it's going to be integral 1 over 4 pi epsilon 0 lambda r divided by y squared plus r squared to the 3/2 dy. What are the integration limits now? Now I have to be careful. A lot of students think the integral should start from 0. Okay? If I actually start the integral from 0, if I take the middle of this line as my first section and infinite as my last section, I would have obtained only half of the contribution, right? So this integral must go from, I should also include negative values. It should go from minus infinity in y to plus infinity. Okay? Minus infinity to plus infinity. So r is a constant. I'm taking it out. 4 pi epsilon 0 are constants. Integral from minus infinity to infinity. 1 over y squared plus r squared to the 3/2 dy. And I get the same questions all the time in Physics 102. You're going to be faced with a lot of integrals. How much of calculus skill do we need in this course? Now the physics content here is not how to evaluate this integral. The physics content is to write it down correctly. However, most of the time we'll be faced with quite simple integrals. Okay, integrals even simpler than this one, like the previous one. So we do expect you to at least understand what an integral means. We want you to be able to express an electric field, a magnetic field, whatever, in terms of an integral as a sum of small pieces. And generally, we do not really measure whether you can evaluate integrals or not. That's generally the math department's job. But still, you've learned something. This is a great opportunity to use your integration skills, right? So let's do the integral. How do we evaluate an integral like this? And it turns out it's not very hard. Okay. Let's do the following. I'm pretty sure you've done this in calculus. Let's think of a right triangle with r base and y height. So tangent theta would be y over r. Now, what will be the derivative of that? 1 over cosine square theta d theta would be 1 over r dy, right? That's great. So how about cosine theta in terms of r and y? Cosine theta is r divided by r square plus y square, right? So the limits, if y is equal to plus infinity, what's theta? Come on, think of the triangle here. Y goes to plus infinity. Theta is 90 degrees. How about y goes to minus infinity? Theta is minus pi over 2. So this whole thing is lambda r over 4 pi epsilon 0 integral from minus pi over 2 to pi over 2. Now the integrand. How am I going to write this y squared plus r squared to do 3 halves in terms of theta? Well, I have a nice expression here. R squared plus y squared square root is r divided by cosine theta. So this is going to be 1 over r divided by cosine theta to the third power. Okay? Is everyone following my substitution? It's not too hard, right? Good. How about dy? I already know what dy is. Dy is r divided by cosine square theta d theta. So it's going to be r divided by cosine square theta d theta. It's great. Lambda r over 4 pi epsilon 0. I have r here, r cubed here. It gives me another factor of 1 over r squared. Minus pi over 2 to pi over 2. I have cosine cube theta divided by cosine square theta d theta. So this is cosine theta. What's the integral of cosine theta? It's sine theta, right? So this is again one of the simple integrals. R, 1 power of r. It's cancelled here. I have sine theta evaluated at pi over 2 and minus pi over 2. So this is sine pi over 2 is 1 minus sine minus pi over 2 is minus 1. So this whole thing is 2. So the end result is lambda over 2 pi epsilon 0. Okay? Well, did I reach my goal? Yes, I've given the direction and the magnitude, and I did not invent any new symbols. Everything is expressed in terms of given quantities. Excellent. How about units? And I'll do this very quickly. I'll just go back to my expression in the quiz problem. It was lambda over 4 pi epsilon 0 d, which had the correct units. What's my expression here? Lambda over 2 pi epsilon 0 times r. R and d have the same units. Should be okay. I reached my goal. I have my units. And how about the limit? What would you expect? Do you expect this electric field to decrease if I go far away? And naturally, I'm getting away from charges. So that's, again, the only limit I can think of. So it makes sense. And it turns out, actually, this is the correct answer. We found the correct answer here. Okay. What would change? So here's the question. I'm not going to solve it. What would change if I asked you to find the finite version? Not an infinite line, but a finite line. Let's say exactly from the midpoint, my distance is r. What would be the electric field here? Let's go over the solution and discuss. Where would I make a change here? It's the limits of integration, right? It will not go from minus infinity to plus infinity. Instead, I would have to go from minus L over 2 to L over 2, which would create somewhat of a problem with the boundaries. It will not go from minus pi over 2 to pi over 2. I would have to express them as arcsines or arctangents of some angle. All right? Good. So this is not a homework, but work this out yourself. Yes?
So what angle are we going to take in solving this question? You said that it is going to be arcsine of some angle.
Yeah, it will be the angle seen. Well, if this angle is alpha, that's going to be the. Any other questions? Okay, so far we've done one-dimensional distributions. Let's make a change, right? Let's solve another problem. Find the electric field on the axis of a uniformly charged disk of radius r and total charge q. So this is somewhat cryptic. Let's actually try to give a plot. What I would like to find out is if I have a disk of radius r and total charge q, and if I'm at a point which is z above the axis, what's the electric field at this point? So does everyone understand the geometry? I have a nice round disk, total charge is q, radius is r, and I'm exactly on the axis of this disk. Again, let's start with the direction. Which direction would the electric field point? Directly up, right? Perpendicular in the z direction. Why? By symmetry. It cannot choose any other direction. All the directions, I can take this disk and rotate it, and nothing would change in the problem. Which means my answer should also be invariant under rotations. So the only thing that can point, the only direction it can choose is along the z-axis. So I'll say by symmetry, its electric field is electric field magnitude times z hat, or we called it k. Right. Now, let's do another calculation. What is the surface charge density on this disk? How did we define surface charge density? Total charge divided by the total area. So it's going to be Q over pi r square. Excellent. But now, how am I going to calculate this magnitude of the electric field? Clearly, I have to break up this disk into smaller units, right? And one kind of unit I have already found the expression of the electric field for is a ring, right? So here is our strategy. What we are going to do is break up the disk into rings. And here I'm actually going to go back hopefully it was somewhere around here. Charge distribution. Excellent. So I will copy this expression. I was not able to copy it. Let's try again. Copy. So, does that feel like cheating to you? No, okay, I did it myself, so I'm not going to admit to cheating. But, you know, if this was an exam question, you would probably either be asked to find the ring's electric field first, so you get some extra points, or you would be supplied by the expression for a ring, okay? And in the future, we'll actually learn quick ways of calculating this expression, right? Now, so this is the electric field of a ring of radius r and charge q. Now, how can I use this to calculate the electric field of a disk? And here's what I'll do. Let me draw a top view of my disk. So this is the radius r. I'll think as if this disk is made up of rings, like an onion, okay, which have radius r and some thickness. So the thickness is dr. Now, can you tell me how much charge do I have small charge in the ring? What's the amount of charge in this ring? Now, if I have any area, what would be the charge in that area? Sigma times the area, right? That was how we defined sigma. So I can write this down. It will be sigma times dA, which is the small area of this ring. So what's dA? I would say it's pi r plus dr. This is the outer circle square minus pi r square. Would that be right? Good. So it's going to be pi r square plus 2 pi r dr plus pi dr squared minus pi r squared. Dr squared. What do you understand from a differential? What's your gut feeling about a differential? How do you think about differentials? Infinitely small, or let me make a physicist definition. They are smaller than any number you can think of, but not zero. Right? So when I think of a differential, I think of a number like 0.000001, and even it has to be smaller than that. So which of these terms is important? Dr or dr square? For any small number, higher powers are always negligible. So this is any differential squared compared to differential itself is, well, not even negligible. It's really zero. Okay? There's another way to calculate this area. Think of it like a simple ribbon. If I cut it and expand it into a rectangle, the thickness would be dr. What would be one side? 2 pi r. So the area is apparently 2 pi r times dr. This only works with differential areas. Those of you who are going to take some differential geometry lectures later in your career would actually learn when one can do this kind of deformation. But that's an easy way to think about it. So what's dq? dq is sigma times 2 pi r times dr. Now, can you tell me what is the electric field this small ring creates? And I'm going to use the expression I've already found. I'll say it's dq divided by 4 pi epsilon 0 times z is still z square plus that r, capital R, in the previous problem was the radius of the ring. What's the radius of the ring here? It's the small r square to the 3/2. Okay? Good. So let's write everything in detail. Sigma times 2 pi r z divided by 4 pi epsilon 0 z square plus r square to the 3/2 dr is my small electric field. What's the full electric field? This will be the integral of these small contributions. So integral sigma 2 pi r z divided by 4 pi epsilon 0 z square plus r square to the 3/2 dr. What are the limits of my integration? The smallest ring I should consider has 0 radius. The largest has capital R radius. Excellent. So it must go from 0 to r. Let's see if this is an easy integral or a hard integral. I'm integrating over r, so z is a constant, sigma is a constant. I already have 2 here, sigma z divided by 2 epsilon 0, 0 to r divided by z square plus r square to the 3/2 dr. And this is again a very easy integral. If I say u is z square plus r square, du would be 2r dr. So this electric field is sigma z divided by 2 epsilon 0. Integration limits when r is equal to 0, u is z square. When r is capital R, u is z square plus r square. R dr is 1 over 2 du u to 3/2. So sigma z over 4 epsilon 0. What's the integral of u to minus 3/2? Any integral u to the n du is u to n plus 1 divided by n plus 1. What's n here? Minus 3/2, right? So this should be u to minus 3/2 plus 1 minus 1/2 divided by minus 1/2. It's z square plus r square. Z square. So let's write this in more detail. Sigma z over 2 epsilon 0 1 over square root of z square minus 1 over square root of z square plus r square. It's not a short answer, but let's check. Did I reach my goal? Not quite, because the statement of the problem had total charge q and r, so I actually have to put q over pi r square here. So it has to be q over pi r square, so I have 2 pi r square z over epsilon 0 1 over z minus 1 over square root of z square plus r square. So now I reached my goal. How about the units? I think it's easier to check in the last form. Q over 4 pi 2 pi r square epsilon 0. This is already an electric field, right? I have epsilon 0 r square down and q upstairs, so this is already an electric field. And I have z, which is meters, multiplied by 1 over meters. So units also check. How about the limits? There's a great limit I can check here. What happens if I go very, very far away? If z is much larger than r, I should get back, I should only see a point charge. And I'm not going to do it because I'm running out of time, but that's exactly what you will find here. And before I actually finish, I would like to solve one more example. I can see some of your friends are going, ah. No. Now let's solve this. I have an infinite plane with charge density sigma. So what is the electric field here? And I'm saying the answer is, okay, now the answer is already on the board. How can I solve this? Did I find out how to calculate the electric field of a disk. What is a disk which has infinite radius? It's a plane. So I can actually, I don't need to solve this problem again. Just r goes to infinity limit of the previous problem. And let me do it quickly. Ez was sigma z over 2 epsilon 0 1 over square root of z square minus 1 over z square plus r square. What is the limit r goes to infinity? The second term just disappears when r goes to infinity. So it's going to be sigma z divided by 2 epsilon 0 1 over z. Z is cancelled. Sigma over 2 epsilon 0. Now this is a somewhat surprising result. It doesn't depend on how far away you're from this plane, but it's an infinite plane, so you can't really gauge the distance. Okay. And this is one result I actually want you to memorize. You don't see lecturers saying that, but I want you to memorize this result. Sigma over 2 epsilon 0 is the electric field of an infinite plane. Right? And next time, we'll actually talk about why this result is so important, how it's going to help us. All right? See you next week.